Q&A. And we're going to move on to our next speaker. Felipe Matas is here. Felipe has had a journey with Postgis Topology. I think it's the same journey that many of us go through, where you find it and you think it's really cool, and then you look for learning materials and try to learn more about it, and you find out that there are no learning materials, and it's really hard to learn. And unlike most of us who just sort of throw up our hands and walk away, Felipe has decided to be part of the solution. He started filling in the topology section of the workshop for Postgis, and he has put together this talk for us today to give us an introduction into Postgis topology. Turn on your mic, Felipe, and share your screen. And here we are.
Yes.
Oh, but I can't hear you.
You can't?
Oh, yep, can. Good. Over to you.
Hello, everyone. Well, someone maybe already know about the Postgis topology extension. And the focus in this case will be about maps, where we can, for example, have countries, states, and we need to work with that maps. But in some circumstances, we can ask ourselves if these maps are correct. They do not have, by any mistake, a free space between the polygons one over the other, which can make really hard time to work with them. I work in the University Adolfo Ibáñez in our research team, the Territorial Intelligence Center, and we're going to see how we use the topology to solve and handle these issues. First, two issues we can think and can be very hard to handle are the overlaps. Is when in our maps we have two polygons, one over the other, and they have a shared space. The issue with this space is that we don't know to who it belongs. So it's from one state, from another, from which country, we don't know. The other one are the gaps. When we draw the polygons, sometimes we make mistakes and between them there is a free space, which belongs to no one. And these type of errors and issues are spread in the maps and very well hidden, so we're going to see how this can impact us.
Hey, Felipe, you're off to a great start. Would you mind speaking just a little bit louder? It's just a little bit quiet.
Okay,
Thank
better?
you.
Before see how this can impact, for example, an algorithm, let's remember our data information, the maps have a meaning. So even an issue can cause misunderstoods in different ways. For example, have a gap or overlap in a country limits, state limits, property limits is very confusing because a state is a political division structure which needs to know of which territory they need to handle or manage. So we don't want that types of issues in these maps. And there is other cases, for example, if we publish safe zones from the territory or risky zones of them, we need a very good map without these issues to let the population, for example, be safe from this. We don't want they to go to the wrong place in any of these cases. From the internal perspective of the territory, any gap and overlap also will contain buildings, facilities, population, any of them. And they need to know to whom they respond because they are also responsibility between them. Going aside of this topic of responsibility, there is also issues if we want to perform basic things like count population. because we have a census, which is polygons or a map of buildings. If there is an overlap, we could count 2 times the same population. If there is a gap, we will basically ignore it. In rural zones, it's even harder because they can be in a very extensive territory, but some small zones will contain most of the population. So here, count more than once or count none of them will have a great impact on our calculations. Now we have a map which could have these issues, but how much can impact different algorithms? Um, there is some of them that can have a great impact. For example, spatial autocorrelation requires spatial contiguity. We can run this algorithm with a wrong map. If we want to intersect geometries, we can end in cases like the population one, where we can, with overlaps, count more than one or non-ignoring part of it. If we want to try, for example, fix this, pick the overlaps and create new polygons, we can have as result the image of a very large polygons with a width of nanometers. If we if we try to run, for example, nearest neighborhood algorithms, they will pick these very weird polygons and the algorithm will give a very bad results, which have no sense. We can also try fix this by hand, but it's also really hard. In the left image, we can see in QGIS everything is fine until we select the polygon above and we found out overlap. The colors do not help a lot. And while we're working with national maps, these issues can be spread in the maps where the width and height can be from kilometers to nanometers. It's really not a easy way to handle it. We'll need a lot of work. Even if we were able to do that, we'll have the main issue, which is while we use simple features, anyone can make a mistake. It's normal. Fixing a polygon or programming, which can cause these issues. To handle these cases in a better way, we can use Postgis topology. The basic concept in which this is created is each simple feature will be of 3 types. We can have points, will be called nodes. When we have 2 nodes, we will create a line string. When in a closed set of line strings, we will have a polygon, which we will call a face. How each line string is a net from each face, we will call them edge instead of line strings. The idea of Postgis topology is an environment where, for example, if you change the position of a node, it will update the edge and the faces. So everything will keep consistent and our information will be valid. One of the things we're going to do that we did here in our work is try to fix the map. We will pick, for example, a gap and try to assign it to a neighbor polygon. This is a reasonable way to fix this issue while they are not have a big extent of territory. There will be better. Very big gaps have other treatment, but we have a limited time right now. What we did on work was try to use topology to handle one of the important data we need and use very all the time. Chile is composed by 3 divisions. The smaller one are the communes, which they build the provinces, which will build the regions. What we are going to do is transform these geometry tables into topology ones. And then using the same tool, Postgis topology, we will build the provinces and regions using the previous topology tables in order to simplify this. We will see them a lot better later. The first to transform a geometry table to a topology one, we need to first create the topology, then create a table. For this, we need first a non-spatial table, and then with a function, add a column to store the topologies. Then we will populate the table. Before everything, we need to have installed Postgis Topology extension and created in Postgres. It's the first step. Usually this comes by default in Ubuntu, for example, so there will be no issue in Linux. So the first step is create a topology. We can choose a name and optionally the projection and position it will use. The topology will store all the geometries we want to load. For example, all the commute geometries will be stored inside here. When it's created, there will be a schema called with the same name we chose, commute topology, and will initially have three tables. The first one, the nodes table, is a trivial one because only have the points and identifier for it. The face table and next data table, they are a little different. To avoid, for example, have the complete face geometry and the edge who conforms the face, they split the work. The face will only have the VBox, which contains all the face, the geometry, and an identifier, while the edge table will contain the line string and how they are all used to construct the faces. Each of these geometries will be called as a primitive, like the minimal unit of the topologies. Create a topology table is actually very easy, but we will check deeper how to interpret this. First, we need a table to store the data, just the commune names, province, and region. And to create a column to store the topologies, we will use a special function where we need to specify which topology to use, the address for the table, choose a column name, and finally, which type of primitives we will use. In this case, will be the polygons for the communes. For now, let's remember the output of this function, which will be layer ID, which is 1. And we'll check deeper what is this later. The tricky part here is that our topology is empty, and we will populate this new table from the geometry table. We can do that in the same way as we copy any table from one place to other. The only difference is that we will use, instead of a geometry element, a topogeometry element. We can perform this with the toTopoGeom function. We passes the geometry, then the topology name, and this weight number with the layer ID, which is 1. This will pick the geometry, transforms two primitives, merge in the topology, and pick these primitives and create a key, which will represent them. And this is the topogeometry. When this table finish, we will have the topology with a lot of information with all the communes and data. And we can also load this table in QGIS in a normal way as any special table. We can also load the topology directly. In the TV Managers option, we can select the schema for the topology, which in this case is Communes Topo. In the schema menu, we can select the Topo Viewer, and we will see, like in the image on the right, the full topology. We can see the faces. We can also choose to see the node, edge, and a lot of different information. To go forward, we need to understand better what Postgis is doing with our elements. A topology, a topogeometries column needs to be created in a special way because Postgis will store all the geometries and group them in something called a layer. The layer is who will store topogeometries, which in each of them will store topo elements. Each topo element can represent a node, an edge, or a face. So from now, we only need to remember the structure. To create any topogeometry, we need to specify to which layer it will belong to keep the relations. What we have done until now is already create a new topology table, which is stored in the layer 1. And we want to build the provinces and regions. But in this case, will be different. The layer 1, the communes, are using the primitives as childs, like a smaller polygons or sections. The communes are the parents. And now we want to build the provinces using the topogeometries of the communes as childs. So we can follow this to create two new tables and do not use primitives nor geometries anymore to build the parents. The idea of this concept and why I am showing first this is that after this is ready, if we fix the communes, we will also fix the provinces and regions because we're using keys. Provinces do not care if any topo element of a topogeometry of a commune changes, while the key is still the same. To perform this, a topo element can also, I didn't show before, represent a topogeometry from other layer. This is the feature we will use to build the provinces and regions. Each topogeometry also knows to which key, to which layer it belongs. So it's needed to create the topogeometry, but when it's created, we can use it globally. Here is very similar as before. We need to create a non-spatial table, then append a topogeometry column. The only difference here is that we need to specify as a new parameter which layer to use as tiles. In this case, it's the layer number 1, which is the communes layer. When this operation finishes, it will say number 2, because the layer we will contain all the provinces will be the layer 2. Here is a big difference. Before we can use geometries to construct the topogeometries, but in this case we'll make a topogeometry from topogeometries. Let's remember that topogeometry is composed by topo elements. So we can cast directly all the communes topogeometries to topo elements and create an array from this. Now we'll be showing more code just because to explicitly show we are grouping by the provinces are the region names. Populate the using the communes is still similar as before. We will insert the province name, region name, and we'll insert this topogeometry. We use the create topogeom function when we need to set the topology name, which primitive will contains, to which layer it will be inserted, and which topo elements will be used as childs. When this finish, we will have on the right all the provinces from the country. Doing exactly the same steps, we can also build the regions table, which will be in layer 3. I will not show it because I think at this step is trivial. We only need to do exactly the same steps. So the layer 1 will be built in primitives and the other ones on the respective layers. Now we can try to fix the overlaps and gaps. To find the gaps in the communes, we can, and we only need to get all the topo elements and know which ones are used more than once. Because if there is an overlap, what will happen? The topo elements, the face, will belong to more than one commune. So when we have this table, we only need to group by, count how many times is used, and then filter with which faces are used more than once. And we can already get all the faces, which are overlaps. We will save this result because we will use it later. To get the gaps is different because the gaps do not belong to any commune. They are formed when we make issues or errors when drawing the polygons. So to get first all the faces, we can look at them in the face table. We only need the identifiers. I like this aspect because not work with geometries directly also makes this very fast. We can cast them to a topo element using an array and then exclude the universal face. Universal face is all that empty space which is out of the country in this case. Always has a ID of 0. Then we'll need to discard all the topo elements that are being used in the communes, very similar to what we did before. With this, we can see on the right where we would have gaps, which we can even not see them in QGIS. I will save these results. Overlaps and gaps has the issue of we don't know to who they belongs. We don't know which commune is the right one for them. So following this interpretation, we can just remove all the overlaps from all the communes because it's the same. And we will transfer them to gaps. This will simplify work because then we only need to fix the gaps and everything will be right. We can do this very easily, iterate over the communes and remove the topo element from each commune. After this, we need to remove the gaps table and create it again because it now will contain the overlaps we already removed. What we want to do is pick any of these gaps, we already know where they are, and assign them to a commune. But there is an issue. We can't just go pick and, for example, remove an edge and be automatically the gap assigned in the commune. Topogeometries are keys to organize the primitives, in this case, the faces. And they have a very hard constraint about how it works. You can only remove an edge if the faces of each side belongs to the same topogeometry. This helps to keep consistent all the topology and do not make any mistake when we're editing them. To follow and do this, we need to perform two queries. In the first one, pick a gap, find the neighbor commune we want to assign, record which edge is in the middle between them, and assign the gap to the commune. We need to wait to the transaction to finish, to the gap be already assigned, and then just pick all the edge we already record and remove from the topology. Now Postgis will allow it. We need to prepare some data to perform this. First, we need to know which are all the topo elements from each commune. So very similar, the same function we use it in gaps and overlaps. We can record the topogeometry and all its topo elements. Second, how we want to merge the gap in a commune, we don't want to look on edge which belongs to the contour. We should exclude all the ones that are in the universal face. The two information from before is for to construct this table. I will not show the code because I think it's more important keep the concept. It's build a neighborhood table. We can look, for example, in the image on the left. We can pick an edge, any of them, record the face ID on the left, and when answer the question of which is the commune who contains that face on the right. So we already know in which edge we will to look on. We already know which faces contains any commune. So we'll often we can easily get these answers. And we will perform the same, but instead of picking and asking from the face of the left, we will ask from the face of the right and get which are the communes that are on the left side. With this table, we can, for any gap, find all the neighborhoods, all the faces neighborhoods from it. Finally, it's just clean the gaps. We will iterate from each gap. We will filter the previous table and know which gap match with a face. And then just limit to one. So we will assign a gap to a random neighborhood common. Finally, when we have the neighborhood table and it's filtered, we only need to add a topo element, the gap, to the topogeometry communes. When this finish, we only need to remove all the edges we before divided the gaps with the communes. When this finish, we will finally have the three tables, the communes ones, province ones, regions ones. And all of the three of them will be valid. Maybe not the official versions, but at least we can use with them any algorithm or use it in a safe way. In this case, we'll fix it only the communes, and the provinces and regions will also be fixed with the previous code. Ideas and future. We already noticed that, for example, maybe will be useful in topology because right now do not have a lot of functions. Make an array of topogeometries, for example, or be able to get the neighborhood of the primitive or of other topogeometries could simplify these workflows. Some ideas that I do not want to take very seriously because can be very hard to organize. I don't know even if will someone like the ideas, will be 3D topologies. I think they could be very useful, for example, extend the dimension to categorize the space. For example, speed of air, or be able to consider topology of mountains, surface, undergrounds, under the sea, tunnels. We could build a lot of things with that. Something that happens, at least in Chile, is that even if the communes are the smaller official division in the territory, each institution sometimes makes its own smaller ways to divide the communes. So I think maybe it will be nice in the future have a way to make a constraint from these other topology sections with primitives, for example, topogeometries of other topology. With this, I finished the presentation. Maybe the last thing is to share in the chat some documents. As Paul, you already said, one of the most difficult sections of topology was the lack of documentation. So in this case, we prepared for this time 2 extra documents which are in the workshop, which is how works internally the primitives and the topogeometries, with a deeper understanding of the concepts, how are built, to construct, for example, our own functions.
Fabulous. Thank you so much for this talk and for all the work you're doing making topology understandable for the rest of us. That was a great talk, and I learned lots. I never thought about how to clean up a data set directly using topology. I always assumed you'd have to do something at build time.